I'm Miles, an electrical and electronic engineer in our biosensing team. I focus primarily on the integration of challenging sensing systems within novel and complex constraints. I have a master's in electrical and electronic engineering from Imperial College London, where I studied a wide range of different electronic disciplines. Those range from digital control systems through to full custom integrated circuit design. With TTP and our clients, I've been developing my skills within sensing systems and developing low-cost electronics even for mass production, as well as integrating NFC into a large range of devices, products, and systems. Integrating biosensors into electronic medical devices is mostly challenged by the design constraints. Inevitably, these are small, wearables or implantables, and they have very tight power constraints, as well as the requirement to have very low noise typically. And we're not talking audio noise, that's electrical noise. These constraints all sort of compete with each other. The small size makes it difficult to achieve good power, whether we're thinking a battery-powered device or something that's wirelessly powered. And we can't forget that sitting on top of all of this are the regulatory requirements. This is still a medical device and needs a risk management procedure. And what falls out of the risk management process are a set of constraints that then sit down on top of both the electronic design, mechanical design, and the system as a whole. And developing that electronic system so that it meets all of your initial design constraints as well as your regulatory constraints is a real challenge. In projects that we've undertaken developing biosensors, getting around our size and power constraints and other system constraints imposed by risk management, we look for novel technologies as well as how we can rapidly prototype them and develop those subsystems to de-risk our main performance concerns and targets within those constraints. So whether that's modeling critical behaviors and trying to understand the physical properties or chemical properties of a sensor so that we can accurately integrate them into a system, or if it's understanding how our risk management procedures will behave and how our subsystems are sitting within that risk management. Recently, we developed a model of a sensing system that required us to generate a statistical model that was based around a custom digital signal processing algorithm that allowed us to relate the effect of input noise to the overall performance and sensitivity of the sensor. This gives us the ability to pull levers on the design constraints and move towards an optimal design that meets our product requirements. We've also integrated and applied cutting-edge thin PCB technologies and layouts for very small biosensor devices. This in itself imposes challenges on how you lay out and design the board, as well as the components you select for the schematic, and how those boards are manufactured, assembled, and ultimately integrated into the device. Our approach to rapidly prototyping and burning down these risk factors and issues and design trade-offs means that our clients reach a design that is most likely to meet their product requirements sooner and very quickly get rid of any looming issues that might arise throughout the development process. I'm lucky to work with a multidisciplinary team of physicists, electrochemists who are able to support me in identifying issues across disciplines and in different areas of a system, so that when working on the electronic system as a whole, I know what needs de-risking and what aspects of the system deserve my focus.